Hello everyone, myself I am Tahira Mazumder, working in AKGEC Engineering College in IT department, and today I'll be talking on the topic of classful addressing and classless addressing, which comes under the subject of computer networks with subject code KCS 603 under AKGEC syllabus. Okay, to start with, let me first discuss about the topics on which I'll be talking. I'll be talking first about IPv4 notation. There are two kinds of notation for IP addresses. One is IPv4 and the other one is IPv6. I'll be talking today in detail about IPv6. Then I'll move on to the range of addresses that comes under I'll be talking about IPv4 and the range of addresses that comes under IPv4. Then I'll talk about the difference between classful and classless addressing, and then the aspects coming under classful addressing, like two-level addressing. Under classless addressing, I'll be talking about CIDR notation, and as we proceed, we'll be talking more in these topics. Now, to start with, let me just talk about what exactly is IPv4. IPv4 is internet. It stands for Internet Protocol version 4, and it is basically a 32-bit address. And what is the purpose of this address? This addresses are used to identify each devices that is connected to the internet. So every device that is connected to the internet has got address. We need to have address to access any like if you compare this to a real world scenario, you want to go to a certain location in a certain city, you need the address. Similarly, whenever we are talking about internet connectivity, we have various devices, various nodes connected to the internet. So to access those devices, to access the various servers, we need the addresses, and the addresses are called IP addresses, and the IP addresses can be of 32-bit. If it is of 32-bit, we call it as IPv4 address, and if it is of 128-bit, we call it as IPv6 addressing scheme or Internet Protocol version 6. So both these topics are having their own pros and cons. They are having some more important points that needs to be discussed further upon. In today's class, we'll be talking about IPv4. Maybe in some other class, we'll be talking more on IPv6. So let us start with IPv4. So as I told you, an IPv4 or Internet Protocol version 4 address, it is basically a 32-bit address which uniquely and universally defines the connection of a host or a router to the internet. So whatever address we are talking about, each of these addresses are unique. They are unique and they are universally visible to all systems connected over the internet. And it is basically, when you're talking about IP address, an IP address is basically the address of the interface. Now, since we are talking about IPv4, so in the case of IPv4, the address is of 32-bit. Now, when I'm talking about a 32-bit address, as I told you, the addresses are unique and universal. And what is the range of the address? If it is a 32-bit address, then what is the range of the address? Now, let us take an example. For example, we are talking about, if you are, let us say we are having a 2-bit number, A1 and A0. What is the range? You will have 00, 01, 10, 11. So that means if it is a 2-bit address, we have how many range of addresses? 0, 1, 2, 3, 4. So you have 4 range, the total range, which is equal to 2 to the power 2. That means if it is 2-bit address, the total range of 2-bit value or address, whatever you are trying to designate it, the total range we have is 2 to the power 2. So similarly, let us say if you are having an n-bit address, then the total range of values in this n-bit address, will say it is of the value 2 to the power n. Now, in this particular example, when you are talking about IPv4, the total number of bits that we are reserving for addressing is 32-bit. So the total range of addresses in the case of IPv4 will be here. The value of n is 32, since it is a 32-bit address. So the total range of address will be 2 to the power 32 minus 1. Why minus 1? Because the addressing starts from 0, 1, 2 and so on. Fine. So the total range of addresses, total values is 2 to the power 32, and if we do the addressing scheme, it goes from 0 to 2 to the power 32 minus 1. This is the final value or the final address of that particular range. And the total number of addresses will be 2 to the power 32. Why so? Because we have 32-bit address, and if we take it, the corresponding equivalent numerical value is this value. So this is the total number of addresses we can have in our internet if we use 32-bit address scheme, which is also called as IPv4. Fine. And next is, so we are talking about addresses which are in 32-bit format. Now the next question is, how do we represent those addresses? Now when you're talking about representing the address, either we go for binary format, which is also called as base 2. In that case, you need 32 number of zeros and ones because 32 bits. So if it's binary form, it need to be, it's something like this is an address which is in binary form. If you see, this is an 8-bit address, this is an 8-bit address, an 8-bit address, all of this. So we have 4 sections of 8-bit addresses, which totals to 32-bit. So when you're talking about how to represent the 32-bit address, either you go for base 2, which is an example of this. So this is a base 2 or a binary number addressing scheme of 32-bit address, or we can go for base 16, which is hexadecimal addressing scheme, or we can go for base 256. Why 256? So because what we are doing is that when you're talking about base 256, that means when you're talking about base 2, that means the values can range from 0 and 1. When you're talking about base 16, the values will range from 0, 1, 2 till it will go till 15. Now when I'm talking about base 256, the values will range from 0, 1, 2 till 255. Now what do you mean by base 256? So what we are doing is that our 32-bit address, the 32-bit address which we have with us, we are dividing it into sections of 8-bit each for our easier representation. We are dividing it into sections of 8-bit each. And so we have, if you look at this example, so we have 4 numbers of 8 bits. This is used to represent what? The 32-bit address. Now what we do is that each of these 4 sections of this 8-bit. So since it is an 8-bit number, what is the maximum range it will go? The maximum range like if you're talking about an 8-bit number, this is an 8-bit number, this is an 8-bit number. So it will range from 0 to 2 to the power 8 minus 1, which is 0 to 2 to the power which is equal to 0 to 255. So if you are taking the corresponding decimal equivalent for each of this 8-bit segments, each of these 8-bit segments will range from 0 to 255. This one will also range from 0 to 255. This one also ranges from 0 to 255, and the first block also ranges from 0 to 255. So the maximum range goes from 0 to 255 for each of the blocks, and hence this form of representation we also call it as base 256 representation, where we are of course using decimal numbers, but the range of our decimal numbers goes from 0 to maximum 255. And why so? Because we are taking 8-bit at a time. So if you look at this example, this is a binary form of representation. This is a decimal form of representation where each of these 8 bits are represented by the corresponding decimal value. Each of these 8 bits are represented by the corresponding decimal values, and they are separated by dots. If you see, they are separated by dots in between. So, and each of these values each of this entire set of values will range from 0 to 255 max, and hence these values are also called as base 256. Why? The values will not go beyond 255. So this is called as dotted decimal representation, this second one, which is also called as base 256 representation. Now we are yet to explain hexadecimal representation. I'll come to that now. Now before that, let us just talk about, here I'll be talking about the hexadecimal representation also. So let us talk about IPv4 addressing scheme, and we will be doing a conversion from one representation to the other representation. Now if you look at it, we are talking, for example, we are having binary notation and we want to convert it to dotted decimal notation, which is also called as 256 base notation. Binary notation is also called as base 2 notation. So if you look at it, since it's a base 2 notation which is binary, so you have, if you look at the totality, you have 32-bit values, 32 numbers of zeros and ones which are in binary form. Now this binary form, what we do, as I told you right now, we basically take 8-bit at a time and correspondingly find out their decimal equivalent. The decimal equivalent of 1000001 is 129. This one is 11, 11, 11, and then 239. So we are converting the decimal equivalent 8-bit at a time, and this is called as the dotted decimal representation. Now let us do the vice versa. For example, you have an IP address which is in dotted decimal notation and you want to convert it to binary notation. Sorry, 2. Here you have a word called 2. We want to convert it to binary notation. So what we have is that we are having numbers which are in decimal notation, which is also called as 256 base numbers. Now what we do is that we take each block which is where the maximum range can go to 256 and convert it by the corresponding 8-bit digit. Convert this by the corresponding 8-bit digit and we remove the dot. And so this is, so that this particular instance is basically the decimal rather we can say this is the binary representation of what? Of dotted decimal. Now let us come to the next one. The next one is hexadecimal form. Now for example, how do you actually go to the hexadecimal notation? How do we represent it? Hexadecimal notation, as I told you here, in this case the base is 16. When I am saying base is 16, the numbers in that particular base ranges from 0 to 15. So when the numbers are ranging from 0 to 15, so in hexa we have numbers ranging from 0 to 15, where we have from 0 for the first 10 digits, we are numbering the digit as 0, 1, 2, 3 till 9, and then we go for A, B, C, D. So this is the 10th digit, this is the 11th digit, this is the 12th, this is the 13th, E is the 14th, and F is the 15th digit. So when you're talking about hexadecimal representation, so our representation of numbers using hexadecimal notation goes from 0 till F, where F represents the 15th digit. Now, so if you look at this representation, the first one stands is 1. If you look at it, so what we do, just give me a moment. What we do is that we now let us come to the hexadecimal representation. So hexadecimal representation has 16, it goes from 0 to 15. That means we have 16 values if you're taking from 0 to 15. So we have 16 values. The range goes from 0 to 15, and 16 means 2 to the power 4. So that means you need to have 4-bit storage capacity for each hexadecimal digit. So what we do, we have this 32-bit number here. What we do, we take 4-bit at a time. Why 4-bit? Because each 4-bit, the range of each 4-bit goes from 0. Why are we taking 4-bit at a time? Because each 4 bits ranges goes from 0 to 2 to the power 4 minus 1. That is 0 to 15. And that is what we are saying. When it comes to hexadecimal numbers, our ranges from 0 to 15. So each 4 digits we are taking and then we are converting that to the corresponding value. So this is 15, and if you remember that previous example where I took, the 15th digit is represented by F. This is 14. So the 14th digit is represented by E. So you take next 4-digit combination. This is 13. The 13th digit, no, this is 8 plus 3, 11. 11th digit is represented by B. Similarly, this is 0. 0 is of course 0. This is again 11. So it is B, and so on. So we take 4-bit at a time. We take 4-bit at a time of the 32-bit address, convert it to the corresponding hexa form, and this is finally the value that we are getting. So this is a number which is in hexadecimal representation, and every hexadecimal representation, to indicate that this is a hexadecimal number, we prefix it by 0x, and or you write base 16 out here. This is one way of indicating that you are dealing with hexadecimal numbers. Here also, since you're doing, okay, that much you do right now. Now let us come to the next one. The next, so we have talked about IPv4 addressing. We have talked about how to represent the IPv4 addressing, and you have said that there are basically three ways. So you go for binary representation, you go for dotted decimal representation, which is also called as base 256, and the other one is you can go for hexadecimal representation, where the ranges go from 0 to 15. Now, let us move on to the next topic. The next topic is we'll now come to classful addressing. We'll talk more on classful addressing, and then we'll move on to classless addressing. Now, what is classful addressing? Now, when you're talking about IP addresses, initially we started the concept of IP addresses with the concept of classes. That means the total range of addresses. We have 32-bit address. So, if you look at the range, we have the range going from 0 to 2 to the power 32 minus 1. This total range of addresses is divided into classes. We have class A, B, C, D and E. So, this total range of addresses are divided into classes, 5 classes, namely A, B, C, D and E, and we call such an addressing scheme as classful addressing scheme. Classful addressing scheme was the first one that came up, followed by classless addressing scheme, which was addressed somewhere in the year 1995. Now, so we will first talk about classful addressing, and then we'll to move to classless addressing, we first have to understand the concept of classful addressing. So, let us understand the concept of classful addressing, and then we'll come to the concept of classless addressing. Sorry, the 1995 is not classful, classless. I'm talking about classless, which came up in 1995. So, we'll start with classful addressing, and then we'll move on to the concept of classless addressing. Now, before we move further, let us just give a brief differentiation between classful and classless addressing. Here in classful addressing, the total range of addresses are divided into 5 major classes, namely A, B, C, D and E. And when we are talking about classless addressing, we replace the classful address. That means there is no such concept of classes. We don't have class A, B, C and so on. We try to go for a method where the concept of class is totally done away, and this helps in minimizing the exhaustion of IP addresses. And what do you mean by that? We'll explain later on. So, this classful addressing is less practical and not that useful compared to the concept of classless addressing. And here the network ID, every address will be having 2 parts, the net ID and the host ID. In case of classful, the net ID and the host ID, the changes depending on the class, which is not the case when you're talking about classless. So, classless is a better version than classful, which overcomes most of the limitations that are there in classful. But to understand classless, we first need to go with classful addressing. Now, let us come to the concept of classful addressing. So, the total, as I told you, we have 32-bit address for IP in the case of IPv4, and if you're representing this entire circle is used to represent this 32-bit address, what we are doing, we are dividing this entire 32-bit address into 2 parts. Fine. So, if you divide it into 2 parts, that means if you have total range is 2 to the power 32. So, if you divide it into 2 parts, you have 2 to the power 31 in one part, and the other part will be 2 to the power 31. So, you have 2 to the power 31 bits in one part and 2 to the power 31 bits in the next part. So, if you look at it, what we are doing, this part which consists of 2 to the power 31 bits, 2 to the power 31 bits, this entire range of addresses, in the first 2 to the power 31 means the first, if you are going for 32 bits addressing, that means from 0 to 2 to the power 31 minus 1 range, it falls under class A. So, class A includes the first 2 to the power 31 values out of 2 to the power 32 values. So, this is the addresses. So, if you look at this figure, class A takes up 50% of the addresses. So, since the total is 2 to the power 32 values, so half of it will be 2 to the power 31 values, and that comes under class A. Now, the remaining half which you have, that again we are dividing it into 2. The remaining half is again, the entire thing is in total 2 to the power 31. If you are dividing it into 2, the values in this section, will be 2 to the power 30, and the values in this section will be again 2 to the power 30. So, what we are doing, the remaining out of the second half, let me again, out of the, so the first half is totally given to class A. Out of the second half, half of it, that means 2 to the power 30 values, 2 to the power 30 values are allocated to class B addressing scheme. So that makes up around 25%. If you look at it, this particular block makes up around 25% of the entire addressing scheme. So this is class B. Now class C, let us come to the remaining part. This remaining part in total is 2 to the power 30 number of values. If you again divide it into two sections, this is the first section, and let us say this is the second section. So if you're dividing this part into two sections, so if you're dividing this part into two, so each part will be having 2 to the power 29, right? So 2 to the power 29 sections, one of it goes to class C. So class C consists of the remaining 2 to the power 29 values, right? Now let us come to the remaining part. Now, if you look at it here, the remaining part, this part is having how many values? 2 to the power 29 number of values. We are again dividing this into two parts. This is the first part and this is the second part. The second part, let me use a different color so that it will be easier to understand, and this is the second part. So if I am dividing it into two, so 2 to the power 29 divided by 2 is 2 to the power 28. So class E has 2 to the power 28 values and class D has 2 to the power 28 values. Class D 2 to the power 28 values and class E has 2 to the power 28 values. So this is how the division is done when you are talking about classful addressing in IPv4. Out of the total 2 to the power 32 range of values of addresses, the first 50% is allocated to class A. Out of the remaining 50%, the first 50% is allocated to class A. Out of the remaining 25% of it are allocated to class B. Out of the remaining 12.5% of it are going to class C, and the remaining 6.25% each of it are going to class D and E. So if you look at it, we are dividing the entire range of 32-bit addresses in 5 classes, and it's very obvious all the classes are not having the same size. Class A has got the maximum range of values, followed by class C, followed by class B, followed by class C, and then followed by class E and D. So how do we find the class of the address? Now if you look at the class of the addresses, let us say class A. So class A has 31 bits. So out of 32 bits, the first bit is made as 0. And the remaining bits will be what? The remaining bits obviously will be 31. So in class A, the first bit will be 0, remaining all of them can be any values. The first bit is frozen as 0. So if the first bit is frozen as 0, so in the first octet, the values will range from 0, 0, 4, 5, 6, 7, 8 till 0, 1, 2, 3, 4, 5, 6, 7, 8. So here the range of the first octet in class A will range from 0 to 1, 0 to 111, 111, which is same as we can say 0 to 127. So in case of class A, the first octet is 0 to 127. For the third remaining 3 octets, it can be any values. Obviously, since you are going for each of these are 8-bit values, so the remaining 3 values by octet values can be 0 to 255, this one also from 0 to 255, this one also from 0 to 255. This is for the range of class A addressing. Now, in case of class B, we are freezing the first 2 bit to 10, and so the same logic applies. If you are freezing the first 2 bit to 10, then so the starting address of this will be 10, since we are talking about 8 bits. So it will start from this and it will end to, because we are freezing the first 2 bit to 10. So this is the range of the first octet of class B, which in decimal form will go to 128 to 191. This is the decimal value, which is 191. So in case of class B, the first octet value will be 128 to 191, which is in the same logic. For class C, the first octet will be 192 to 223. For class D, it will be this range and so on. So that means whenever you look at an IP address, and for the other octet, what are the values? Obviously, since we are taking the entire 8-bit, each of these other octets will range from 0 to 255. Each of the other 3 octets will range from 0 to 255 because we are taking up the entire 8-bit space. Only difference will be in what? The only difference will be in the first byte or the first octet. So when the first byte, so how, if you look at an IP address now, how do you identify to which IP address does it belong? What you do is that you first look at the first byte and see what is the range. If the range is within 0 to 127, we'll say it is a class A. If it is from 120 to 191, we'll say it is class B, and so on. So this is how, looking at IP address, you can say to which class does it belong to. So the logic is, if you want to differentiate how to identify, you start, what you do is that you check the first bit. You see if the first bit is 0, that means it's a class A. If not, if the first bit is 1, then check whether the next bit is 0. If the next bit is 0, then it is class B. If not, then first 2 is 1. Then you go and check whether the third bit is 1, and if the third bit is 1, it is class C. If not, that means it is what? If not, that means it is 1. It's all 3 ones, and then check whether the next one is 0. If it is next one is 0, it is class D, or else it is class E. So this is another way of looking at the same thing. So this is how we have divided the entire 32-bit space. We have divided the entire 32-bit space into 5 classes. So in case of classful addressing, where we have already said that we have got 3 classes. Out of the 3 classes, we have got 5 classes basically, A, B, C, D and E. Out of the 5 classes, the first 3 classes are used for addressing, and the remaining 2 classes are reserved for some special meaning, which we'll be talking more about that maybe in some other classes. And so what we're doing, each IP address is basically divided into 2 parts, the net ID and the host ID, and these 2 parts are of varying length depending upon the kind of address we belong to, whether we belong to class A, B, C or D. Now we already have said D and E are reserved for special purpose, and they don't fall under the category of being divided into 2 parts, the net ID and the host ID. So division is something like this. If this is the entire 32-bit address, what we do is that we divide it into 2 parts, the net ID and the host ID. The net ID is used to identify, the net ID is used to identify the network to which the system belongs to, and the host ID is used to identify a host inside the network. So now, so that means out of the 32-bit, as I told you, IPv4 is in total, it is made up of 32-bit. So out of the 32-bit address, we divide into 2 parts. So let us say if we are dividing n bits, we are taking n bit for representing the net ID. The remaining will obviously be 32 minus n bit for representing the host ID. So this value of n will differ based on which class of addressing we are using. So if we are, let us say, if we are looking into class A, the value of n is 8. That means 8-bit address will be used. 8-bit will be used for the net ID, and remaining 32 minus 8, that is 24. 24-bit will be used for the host ID. In class B, 16-bit for the net. So remaining out of 32, we have left with 16 more. So 16-bit for the host, and class C, 24. So 24-bit for the net ID. Something like this. If you look in the figure, this will more clear. It will be more visible. 8-bit for class A, 16-bit for class B, and 24-bit for class C. And class D and E are reserved for special meaning. Normally class D is used for multicasting, and class E is reserved for future use. So we are left with the first 3 addressing, class A, B, C, for our addressing scheme. So what we do is that, if you look at the addressing scheme, what we do is that we divide the address into 2 parts, the net ID and the host ID. The net ID is used to represent the network address, and when you're representing the network address, there are 2 addresses which have got spatial meaning. The spatial meaning is net ID with the host ID as all zeros and with the host ID as all ones. If you remember, if we are talking, let us say we are talking about class A addressing, in this case, the net ID is of 8-bit and the host ID will be of 24-bit. So in class A, all zeros means 24 number of zeros, and here all 1 means 24 number of ones, fine. So this is 2 spatial values which have got special meanings. In this case, when the host ID is all 0, we call it as the first address of the network, or this is also the address that is used to indicate the entire network, or rather we can say the entire network is identified by this address. And when all bits of the host ID are 1, we indicate that it is a last address, which is normally used for broadcasting. So, as I told you, the range of addresses allocated to an organization, they are normally falls under 3 categories, A, B and C. Now, let us move on to classless addressing. So, in classless addressing, as I told you, classless addressing basically tries to overcome the drawbacks of classful addressing. And what is the drawback? If as I told you here, if you look at this figure, Class A is taking up entire 50% of the addressing, and in Class A, if you remember, net ID is of 8-bit and host ID is of 24-bit. That means we can have maximum 22 to the power 8 number of networks if you are using Class A, and the number of hosts can be in each network is 2 to the power 24, and 2 to the power 24 number of hosts is a huge number. That means in each number having 2 to the power 24 number of hosts is practically not possible to make a network using this number of hosts. Similarly, for Class B also, that means we are getting a restriction. The restriction is if you are following Class A, you only have 8-bit at your disposal to form the network, or rather you can maximum form 2 to the power 8 number of networks with 2 to the power 24 hosts in each network, which is also not a very good number, not a very practical number. Similarly, if you are going for Class B, you can have 2 to the power 16 number of network addresses, and inside each network we can have maximum 2 to the power 16. So, but if you don't use 2 to the power 16, maybe 2 to the power 16 means 1024 into 2 to the power 16. So, 2 to the power 16 is a huge number. We may not exhaust all the addresses. So what happens is that classful addressing leads to wastage of addresses, because out of the entire range, as I am saying, every address has got 2 parts, the net ID and the host ID. As we just right now studied. Host ID, for example, if you are using Class A addressing, 8-bit for the net and 24-bit for the host. We may not need 24 bits for the host. So, in that case, what is happening? We are wasting the remaining bits which are not needed, because classful addressing is very rigid. You can only choose one among this A, B, C. So, this leads to the wastage of all the addresses that are given to us, and most of the addresses may not be useful. To overcome this drawback, basically we come to the concept of classless addressing. So, in classless addressing, what happens is that, let me move on, just give me a moment. So, in classless addressing, basically we do away with the concept of reserving the bits for the size for net ID and host ID. Classless basically is an improvement of IPv4. It is an improved version, and we can say it like this: first it was classful, then we moved on to classless addressing, and then we moved on to IPv6, which is a better version. So let me talk a little bit more on classless addressing. Here we don't have net ID and host ID reserved. We don't have reserved size for net ID and host ID, unlike classful addressing. Here the whole address space can be divided into variable length of blocks, okay, and we can have blocks of any size. It can start from 0-bit to 1-bit to 3. That means when you are talking about net ID and host ID, the size is not fixed. The number of bits for net ID can either be 0-bit, 1-bit, 2-bit, or it can go to 32-bit. So this is a classless addressing basically provides us variable length of blocks, which is quite an advancement. It does away lots of the errors, lots of the lacunas and drawbacks which we have with classful addressing. And so, out of this, an organization can be granted number of blocks as per its requirement. So the question of wastage of the addresses does not arise when you go for classless addressing. So this is the look of it, how it looks like. So we can say something like this. So we have this concept. The same thing is there as we have said in classful. Only thing is that we don't have strict definition, like for classful. In classful, for Class A, the value of n was 8. The value of host ID was 24. Here it is nothing like that. N is a variable unit. So obviously, whatever prefix value you choose, the value of n can be any value, 0-bit, 1-bit, 2-bit. It can go from any 0 till 31. So 0 till 30, since we are talking from 0 till 32, of course. So whatever number of bits you are reserving for the prefix, which the net ID, which is also called as a prefix, the remaining will be the 32 minus 1. So the rigidity, the fixed rule that we were following in class full addressing of having the number of bits reserved for net ID and host ID is done away with in classless addressing, and we have lots of flexibility here, leading to less wastage of address space. So this classless addressing is also called as CIDR, that which stands for classless interdomain routing. Fine. So in this case, what we do is that we go for slash notation, because what we do is that we go for the 32-bit address. We have the 32-bit address. Since it's a variable thing, how will you know what is the number of bits reserved for network and how is the number of bits reserved for host? So to understand that, we prefix it by n. We prefix it by n. So the prefix part tells the number of bits that is used for the network, and the remaining part will tell the number of bits that is used for host inside the network. Let me explain here. Like for example, we have an address something like this, 171, let me put it like this, 123.15.8.7 slash let me say as 20. What does it mean? It means this n tells the number of bits that is reserved for prefix, or rather that is reserved for the net ID. So out of the total number of bits, 20 bits is reserved for net ID. That means here, if you remember, we have 8 bit, this is for 8, 16 bit, and from here it will take 4 more bits. So out of this entire 32-bit address, out of the 32-bit address, 20 bit of it will be taken up and reserved for the net ID. What we are left with, the remaining we are left out of 32, we are left with 12 bit. The 12 bit will be used for identifying the host ID. So it's a variable thing. How many bits do we have for the net ID and how many bits we have for the host ID will be designated by the value of n, which will vary from time to time. So we are doing away with the restriction that was imposed by classful addressing. Here this one is variable and we can address the block size as per our requirements. Based on that, we will change the value of n. So this is just a brief comparison between classful and classless addressing. In some of the class, maybe in some of the lectures, I'll be talking more about class A, B, C and D, what exactly happens in those classes. Right now, because of time constraints, I'm not able to take it right now. So next class, I'll be talking more on that. So for the time being, I'm winding up. These are the reference books that I had taken up by Firozan, by Tenenbaum and by Kuros and Ross. Thank you.